Mercedes-Benz Stadium is not merely a sports facility, but a world-class complex structure that embodies advanced engineering and precision structure analysis. Its retractable roof and asymmetric truss system generates significant loads in both vertical and horizontal directions, necessitating a specialized construction strategy to safely transfer these complex forces to the ground. Starting with foundation planning based on site conditions, we will explore how each part is connected and why each construction method was selected, tracing the flow of the structural logic and construction strategy. Mercedes-Benz Stadium is an ultra-large-scale structure that required the safe transfer of complex loads, including roof truss loads, lateral forces, and the weights of retractable roof system to the ground. Due to these unique structural demands, conventional foundation and column systems were insufficient. Each male column, which directly supports the roof system, was required to withstand loads up to 37,000 kN. To resist this, a combined structural system utilized the mat foundation and mat columns were adopted. To reliably support the high axial loads from the mat columns, a massive mat foundation approximately 3.5 meters in depth was constructed. Before concrete pouring, the foundation included 1.83 meter diameter drilled piles and auger cast piles, and temporary supports were installed throughout the entire foundation area to ensure construction stability. After pile installation, 600 mm spaced cover blocks were placed to maintain the required concrete cover, preventing rubber from contacting the bottom or walls. Especially at mega column locations where load concentration is extreme, vertical support type spacers or custom steel jigs were used instead of flat type blocks to ensure precise placements. At the bottom of the mat foundation, main rubbers approximately 60 mm in diameter were densely arranged in a 300 mm orthogonal grid. These rubbers were fabricated and transported in 12-meter lengths and were lapped on site using the rubber lapping technique to accommodate extended spans. This method involves overlapping rubbers by at least 40 times their diameter, approximately 2.5 meters, to ensure continuous stress strength transfer within the concrete. The overlap sections were tied with steel wires for stability. The mat foundation was reinforced in 4 horizontal layers, bottom and top mats, along with 2 intermediate layers. Each layer was spaced at roughly 2 meters using chair rubbers to maintain precise vertical alignments. Additionally, extra top rubbers were placed over the top layer to enhance crack resistance and structural continuity. Construction was supported primarily by crawl cranes and boom pump cranes. Crawl cranes handled the transport and assembly of rubber cages and formwork, while boom pumps were used for large volume concrete pouring over board areas. In some cases, multiple pumps operated simultaneously to place hundreds of cubic meters of concrete in coordinate zones. These cranes played a vital role in ensuring accuracy and construction efficiency throughout the process. Once all rubber placement was completed, the concrete was poured to complete the mat foundation. Installed above the foundation, the mega column served as critical vertical structure designed to resist not only gravity loads from the roof trusses but also significant lateral and dynamic forces from the retractable roof system. Each male column stands approximately 31 meters tall. Due to concerns such as hydration heat control, internal concrete pressure, and safety during vertical construction, the columns were not poured in one continuous lift. Instead, they were lifted into vertical segments. Each segment measured 3 meters in height, and subsequent pours were carried out after 24 to 48 hours of curing. Mega columns feature densely arranged vertical rubbers. These bars had a diameter of 57mm and a yield strength of 500 megapascal placed at intervals of 100mm. At the corners of each column, the spacing was even tighter to resist flexural moments more effectively. Placing the bars toward the corners all ease concrete placement by avoiding conjection at the core. To resist shear forces, prevent main rubber buckling, and ensure seismic performance, horizontal stirrup rubbers were installed. Given the stadium's massive structural loads, these stirrups were both thicker and more densely arranged than in standard RC columns. Rubbers with a diameter of 90mm were used, spaced every 100mm at the lower sections and 200mm at the upper level. Once the reinforcement was completed, formwork was installed, starting from inside then the outside. The formwork consisted of modular segment panels. After each pour, and once the concrete reached 70 to 80% of its design strength, workers entered the core and dismantled the internal formwork using a sliding method. The panels were then lifted out using tower cranes. Following the removal of inner forms, additional concrete was poured inside the hollow section. Each segment was poured in 3-meter increments, and the same forces were repeated layer by layer. Through this construction sequence, the mat foundation and mega columns were structurally integrated, enabling the effective distribution of both vertical and lateral forces from the roof system down to the ground. As a result, a structural system capable of supporting loads up to 37,000 kN per column was sufficiently implemented, balancing durability, construction efficiency, and long-term maintainability. Columns are essential structural elements that transfer vertical loads throughout a building, and in high-rise or large-span structures, their stability and durability are critical to the overall performance of the structure. However, simple placing reinforcements and pouring concrete is not enough. To maximize column performance, detailed reinforcement strategies such as proper lap size, lengths, stirrup bends, angles, and alternating hook directions must be precisely followed and executed. When rubber is spliced by overlapping, it is critical to ensure proper distribution of these splices. Specifically, no more than 50% of longitudinal reinforcement is any given cross-section of a column should be spliced at the same location. Next, let's discuss lap lengths, the lengths over which two reinforcing bars are overlapped to ensure sufficient strength transfer from one bar to the another. For the lap splice to be effective, the overlap portion must be long enough to develop the required bone strength. A key detailed requirement here is the adoption of a 1:6 slope in the splice configuration. This slope ensures a gradual stress transition and reduces the risk of splitting failure along the concrete. In some cases, achieving the proper lap geometry may involve controlled bending of the bars to maintain both spacing and alignments. Now let's turn to transfer reinforcements. More specifically, tie bars or stirrups, which confine the vertical reinforcements and enhance the column's resistance to lateral loads. It is essential that the hooks at the ends of these ties are bent to a 135-degree angle. Improperly bent ties, for instance those with 90-degree hooks, are significantly less effective in confining the core concrete and can lead to perpetual failure under clinic loading. Lastly, it is important to consider the orientation of the tie hooks. All tie hooks should not face the same direction. Instead, the hook directions must be alternated or staggered around the column perimeter. This practice provides more uniform confinements and eliminates directional bias, thereby improving the overall ductility and load resistance of the structure members. The structural system of Mercedes-Benz Stadium is not simply a combination of individual elements, but the result of a fully integrated approach that considers load paths, construction sequences, material properties, and long-term stability as a unified whole. As a result, the stadium is able to maintain structural integrity even under extreme conditions such as earthquakes, high winds, and large crowd loads, and is recognized globally for both its engineering and architectural excellence. Ultimately, this project demonstrates that a well-coordinated construction strategy is not just about assembling components, but about designing how the structure behaves and performs as a unified living system.